All right, welcome students. Today's goal, we're going to analyze polynomial graphs. And right here, this very first topic, it's called general shapes. So as we've been studying functions throughout this course, here's three that you should know already, right? Let's actually start with kind of the most recent one. You know if a function is quadratic, meaning it has an x squared, the general shape that's going to make is this parabola, okay? Now listen, general shape means not every single parabola is going to look exactly like this, right? You could have an upside down parabola, you could have a real skinny parabola or a very wide parabola. So not every parabola looks the same, but generally we can say a parabola makes this kind of U-looking shape with the vertex, okay? Now, kind of going backwards from there, one of the most basic functions in all of algebra is the linear function. This would be a function whose highest term is an x. And once again, not every linear function looks exactly like this. Sometimes the slope goes down, sometimes it's a steep slope, sometimes it's a very flat slope, right? So there's different types of lines, but generally we can say a linear function looks like this. It makes a perfectly straight line, no curves. All right, and here's one. If the degree is equal to 0, that means there's actually no x whatsoever in the function. If the function doesn't even have an x at all, okay, then it's going to make a horizontal line like this. So hopefully you already know the general shapes of these three functions. Okay, what might be a little bit new to you is, what about cubic, quartic, and quintic? Okay, a cubic function means that the highest term in that function is an x to the third power. Now, not every cubic function looks the same. You're going to see a lot of variety. But generally speaking, with a cubic function, you're going to get this kind of, sometimes I'll call it like an N shape. A lot of students think this looks kind of like a wavy N, the way it goes. Now, again, not every cubic function is going to look exactly like that. Sometimes your N shape goes kind of in the opposite direction. Sometimes it's steeper, sometimes it's flatter. But generally, we can say cubic functions look like this. Now, likewise with quartic, which means the top term is an x to the fourth, or quintic, where the top term is x to the fifth. What happens with each of these is every time you go up a degree, you add another curve to the function. So whereas cubic kind of had like two, you call them turning points, Quartic's actually going to have three. Sometimes students say that this kind of looks like a W shape. But you can look, there's a turning point, 1, 2, 3. And sometimes the turning points are more obvious than others, but at most, a quartic, and generally a quartic function is going to have these three turning points. And so that means quintic actually, we're going to add another curve in here. Instead of just going like this, we add one more curve. Sometimes students will say this kind of looks like a two-humped camel, a camel with like two humps here. Okay, so these are called the general shapes. Not every function is going to look exactly like this, but generally, this is the shape that we're going to get. You'll notice quintic actually has at most four turning points. Now the next topic here is end behavior. So end behavior has everything to do with the arrows at the end of your functions. Do they go up or do they go down? Now if you look back at your general shapes here, like when the degree is 1, you'll notice like one arrow goes down and one arrow goes up. If the degree is 2, both arrows here are going up. If the degree is 3, one arrow goes down, one goes up. If the degree is 4, both arrows go up. If the degree is 5, you have one arrow goes down, one arrow goes up. Well, you can make some generalizations about what you see here. Anytime the degree is even, so that would be like second degree, fourth degree, sixth degree. If the leading coefficient is positive, you're going to get arrows that look like this. Both arrows are going to go up. Okay? And the rest of the graph, you don't know exactly what's going to happen in between the two arrows, but here, if the degree is even, and the leading coefficient is positive, both arrows are going to go up. Now compare that to if the degree is even, but the leading coefficient would happen to be negative. Okay, so if instead of an x to the fourth, let's say, just pretend this was a negative x to the fourth, What actually happens in that case, both of your arrows would go down, like this. Okay. Now with the odds, with the odd functions, with the odd degrees, you're always going to get an alternate where if the degree is odd and the leading coefficient is positive, one arrow is going to go down, the left arrow is going to go down, and the right arrow is going to go up. Now if you make the leading coefficient negative, so and that's exactly what we have here. This arrow goes down, the left arrow goes down, the right arrow goes up. Now if you were to switch it and make this like a negative x to the third, that actually would get switched, where the left arrow would go up and the right arrow would go down. Okay, now I'm going to fill in some kind of fancy words here, and I'll explain them in a bit. So as I write out this right here, what I wrote here in blue, this is called the end behavior of a function. Now here it is in very simple language. Both of these arrows go up, so we say it goes up to the left and it goes up to the right. Compare that to here. Here we have this arrow goes down and this arrow goes up, so we say down to the left and up to the right. When you give end behavior of a graph, you're always going to have two lines. The first line is going to tell you what happens to the left arrow. The second line is going to tell you what happens to the right arrow. Now lastly, we're going to add in our notes here. Okay, end behavior up here where I use this little like, where I use this language here, this is called the simple way to write the end behavior. The graph goes up to the left and it goes up to the right. Now there's also a more academic way to write that exact same thing. Here's the simple way to write end behavior, and right here in this box, this is the more academic way to write it. Here you're saying the function approaches positive infinity as x approaches negative infinity. We'll break that down. That just means the function goes up as x goes to the left. And then the second line says the function f of x approaches positive infinity as x approaches positive infinity. Put this in simple language, this means the function goes up to positive infinity as x goes to the right towards infinity. All right, so in these boxes, this is another way to write end behavior a little bit more academically. And we'll kind of translate one more. Here it's saying the function goes down to negative infinity as x goes left to negative infinity, or the arrow goes down to the left. Here you're saying the function goes up to positive infinity as x goes to the right to positive infinity, or the arrow goes up to the right. So your assignment is going to kind of switch. Sometimes it's going to use this really simple language to use end behavior. Sometimes it'll use this more complex symbols in this box. The main thing you need to remember with end behavior always has two lines. The first line tells you what the left arrow is doing. The second line tells you what the right arrow is doing. Now another generalization you can make about all these functions is this. If your function is of an odd degree, meaning it's either first degree or third degree or fifth degree or seventh degree, it is a guarantee that that graph will have an odd number of zeros. Okay, so you think of like any line. Any line is going to cross the x-axis once. It would have 1, 0. And think of like a cubic equation. A cubic equation could easily cross the x-axis 3 times. You could see how that could possibly cross the x-axis like 3 times. Okay, and there's no guarantee as to exactly how many zeros a odd function will have, but it will always be an odd number. So here you could have like a quintic function with a lot of twists and turns that hardly ever crosses the x-axis. Okay, you can imagine something like this. But as long as this arrow is going down and this arrow is going up, or some variation of that, there's always going to be an odd number of zeros. So like this function had 1, 0, this function had 3, this function had 1. No matter what, if your function is an odd degree, it will always have an odd number of zeros, meaning it will either have 1 or 3 or 5 or 7, etc. Now with even degree, the only guarantee with an even degree function is that it will always have an even number of zeros. So you imagine this would be things like x squared or x to the 4th. So you can imagine a parabola, since both arrows are either going to ultimately go up or both arrows will ultimately go down, there's always going to be an even number of times it crosses the x-axis. So here this parabola crosses the x-axis twice. Okay, and you can add some curves, and you don't know exactly where those curves might end up. So here's an example of a quartic. But it is a guarantee there will always be an even number of zeros. So here again you have a quartic, it crosses the x-axis twice. And I do want to point this out real quick. Even if you had a parabola that came down and touched the x-axis and the vertex was right on the x-axis, sometimes students will argue, they'll say, hey, Mr. Klein, what about this? Here's an even function, it's a parabola, but it only crosses the x-axis once. Well, believe it or not, if your vertex bounces off of the x-axis, this is actually called a double root or a double zero. That actually counts as 2 zeros. If the vertex bounces off the x-axis, you have to count it twice. Okay, so all of these here had 2 zeros. You could easily see how you could also have a quartic that had, like, if the x-axis was right here, you'd have 1, 2, 3, 4 zeros. But no matter what, if it's an even degree, the number of zeros is also going to be even. All right, and the last thing to look at before we do our examples is the number of turning points that a graph has. So if any function is nth degree, it's going to have at most n minus 1 turns. Okay, so what that means, if it's a third degree function, then at the most you take 3 minus 1, it's going to have 2 turns, at most. Okay, it could sometimes have less than that, but at most it's going to have 2 turns. If you had a fourth degree function, it's going to have at most, you take 1 off of that, it's going to have at most 3 turns. And let's kind of look at our general forms to verify this, right? So if it's third degree, look at this. You can see the 2 turns. At the most, it's going to have 2 turning points. Okay. Now sometimes you have a situation where it would have less than that. Sometimes you have the end shape kind of flattens out like this. Okay, so sometimes you could argue, well, it has less than that, but at most, x to the third is going to have 2 turning points at the most. X to the fourth, on the other hand, it's going to have up to 3 turning points. Here you have this is kind of like the number of vertexes that it has. Here you have 1, 2, 3. X to the fifth degree could have up to 4 turning points. Okay, you get the idea. The formula is simple. If it's nth degree, you take 1 away from that, and that's the maximum number of turns that it could have. All right, so with all of that information, let's get into some examples. For each function, determine its degree, its end behavior, the number of real zeros, and the maximum number of turning points. All right, so I'm looking at example number 1. So here we just have the function. There's no graph to look at. You could type this on Desmos if you wanted to, but you don't have to. The degree is 4th degree, or we'll say quartic. Now let's look at the end behavior. So here, this is clearly an even degree. 4th is an even number. But notice that the leading coefficient here is negative. The LC, the leading coefficient, is negative. It's negative 3. And so here's where I just look at my chart. If it's even, if I have an even function with a negative leading coefficient, both arrows are going to go down. And you could either word it like this, down to the left and down to the right, or you could write this fancy notation. Depending upon what the assignment's asking you, I think it'll probably even be multiple choice. I'm just going to go the easy way. Down to the left, down to the right. So I haven't even looked at the graph of this yet, but if I were to type this into Desmos and graph it, guarantee you both the arrows are going to end up going down. All right, part C says the number of real zeros, is it odd or even? Well, this is so easy. Since 4th degree is even, I know it's going to have an even number of zeros. And this last one's really easy too. If it's 4th degree, if we take 4th degree minus 1, we get maximum 3 turns. Okay, so I didn't even look at this graph, but I have an idea. Since it's quartic, I know both arrows are going to go down. I can make a general idea of this graph. It's probably going to look something like this, where it has 3 turning points. Both the arrows are going down. And I don't know how many times it crosses the x-axis, but it's going to be an even number. Yeah, it's either going to be 0 or 2 or 4. All All right, now let's do one where we actually have the graph. So here, we do have a graph to look at. We'll look at your general shapes. This looks very much kind of like a backwards N shape. The general shape looks very much like this. It's just kind of in reverse. Well, that's called cubic. Okay, so the degree on this, it is third degree, which is cubic. And listen, here, they tell me the end behavior. This arrow goes up, this arrow goes down. We say it goes up to the left, down to the right. Up to the left, down to the right. That's called the end behavior. The number of, the number of real zeros is going to be odd. Since third is an odd number, the number of real zeros is going to be odd, and you can actually count. It has 1, 2, 3 zeros, which is an odd number. And then the maximum number, here, go back here to see what these were. The maximum number of turning points, all we do is we take third degree minus 1. Third minus 1 equals 2 turns at the most. And if you look at what are basically the kind of the vertices, the vertices you could say, there are in fact 2. All right, last example we'll look at. Okay, so here we have another one that's just a function. Okay, so the degree, this is a 5th degree, or you could say quintic. Part B says, what's the end behavior going to be? Well, here, the leading coefficient is positive. You can imagine there being a positive 1 here. So if I have an odd function, 5th degree, with a positive lead coefficient of 1, your chart gives you this answer. Odd degree, positive leading coefficient. This arrow is going to go down. This arrow is going to go up. I'm going to write that the simple way. Down to left, up to the right. That's called the end behavior. And since 5th is an odd number, I know that this graph's going to cross the x-axis an odd number of times. And then the number of turns it's going to have is going to be the 5th degree minus 1 equals 4 turns at the most. All right, so hey, hope this was helpful. Best of luck on your assignment and take care. Bye.